Okay. Good afternoon, all of you. Welcome to this lecture of applied thermodynamics. So, in last lecture, we started the chapter number 3, that is vapor power cycles, right? So, as the name of your subject is applied thermodynamics. So, up to this point, we have covered the basics of thermodynamics. Now, we are going into the application part, right? So, the biggest application for the thermodynamics, as it can be, that is a power plant, a thermal power plant. Okay, and in this subject we are going to study, or in this chapter we are going to study how a thermal power plant works, how to calculate its efficiency, how to improve efficiency of a power plant, right? So the basic cycle for that power plant is vapor power cycle. So in last lecture we have seen the cycle which gives you maximum efficiency, that is called as Carnot cycle. Then Carnot cycle, we have seen the limitations of Carnot cycle. We cannot practically implement the Carnot cycle. So that is why we have Rankine cycle. Rankine cycle is what mostly widely employed or applied for the vapor power cycle. Okay. So first I will take the revision of last lecture and then we can start. Okay. Okay. So last lecture we started. Okay. So we started with the Carnot cycle, right? Carnot cycle is the cycle which gives you maximum efficiency for a heat engine. In that, we have seen in a Carnot cycle, we have two isothermal processes and two isentropic processes. So 1 to 2 process is a constant temperature heat addition. 2 to 3 is a isentropic expansion, or where the work is done. 3 to 4 is a constant temperature heat rejection in the condenser. 4 to 1 is a isentropic compression in the pump or in compressor, right? So this was the Carnot cycle. It gives you maximum efficiency, but it has some practical limitations. Why? Because the isothermal processes are very slow and isentropic processes are very fast. So one process is very slow, one process is very fast. So that is practically not possible. So for that we have a Rankine cycle. Okay. So many of the impracticality associated with the Carnot cycle can be eliminated by superheating the steam in the boiler and condensing it completely in the condenser. Okay. Last lecture I have told you, for a turbine to operate efficiently, we need to supply a superheated steam. If we supply wet steam, that means steam with some water particles, that water particles corrode the blades of the turbine, and that is why we do not want to decrease the efficiency of turbine. So that is why we supply the superheated steam to the turbine. Okay. So in this case, in Rankine cycle, we superheat the steam and we completely condensate it into the condenser. The ideal Rankine cycle does not involve any internal irreversibilities. That means there is no fluid friction, there is no pressure drop, etc., etc. In this case, let us see processes 1 to 2 is again isentropic compression, but in pump. 2 to 3 is a constant pressure heat addition in the boiler. 3 to 4 is an isentropic expansion in turbine, and 4 to 1 is a constant pressure heat rejection in condenser. Okay. Right. Then we have seen how to calculate the efficiency of the Rankine cycle or a power plant working on ideal Rankine cycle. So efficiency, as I told you in last lecture, in numerator we always go for the what was our objective of that project, and in denominator we go for the available inputs. So objective was to do some work, so we take the net work. So net work is work done by turbine minus work required to run the pump. So WT minus WC, that will be net work done, and divided by heat input, here it is QH. Whatever heat we received in the boiler, that will be in the denominator. So efficiency formula is in front of you. W net divided by Q in will be equal to turbine work minus pump work divided by Q in or QH. Now next. So today and in last point, in the last lecture, we covered the actual Rankine cycle. What you see, 1 to 2 to 3, 3 to 4, 4 to 1, that is a ideal Rankine cycle. But due to the irreversibilities, and heat loss to the surrounding, there is a change in actual, or there is a deviation from the ideal cycle. So in the pump 1 to 2, what happens due to the irreversibilities, fluid friction, the entropy increases. So that is why we get a 1 to 2 dash. Okay. So here it is. On the second diagram, you can check 1 to 2s was the theoretical one, but 1 to 2a is the actual one. Again, 2 to 3, in this case, again in the boiler, as the water flows, there is a pressure drop along the length of the tube. Again, we get a pressure drop. So you can see here, this is a pressure drop in the boiler tubes. Next is turbine. In turbine also, it is assumed, theoretically it is assumed it should be isentropic. That means the entropy should remain constant. But in actual, what happens? There is a increase in entropy due to the irreversibilities, right? Due to fluid friction, etc. The entropy of the outcoming steam increases. So we get a new line, that is a 3-4, this dash line. Again, the steam passes through the condenser. In condenser, we have tubes. As it passes through the tubes, there's a drop in pressure. So that is why we get a 4 to 1, like an inclined line. So this is ideal, and then the dashed lines show the actual Rankine cycle. So in order to compare between these two, we have a term called isentropic efficiencies. Isentropic efficiency for a pump is the actual, the theoretical work required divided by actual work required, and isentropic efficiency for turbine is actual work done divided by theoretical work done. Okay, so this way we calculate the isentropic efficiency. So there will be numericals on the isentropic efficiency. Also, there are some MCQ questions are asked based on isentropic efficiency. We'll cover it later. So that was about the last lecture. Okay. Now, today we'll see how to improve the efficiency of the Rankine cycle. So the basic idea behind all the modifications is to increase the thermal efficiency of the power plant is the same. So what is the basic idea? Increase the average temperature at which heat is transferred to working fluid in the boiler, or decrease the average temperature at which heat is rejected from working fluid in the condenser. So there is a term called mean temperature of heat addition in the boiler. Whatever mean temperature, average temperature is there, that is called as mean temperature of heat addition. So there are two ways. Either you increase the temperature at which heat is added in the boiler, okay, or you decrease temperature of condenser, temperature at which steam is converted into water. So again, you cannot just increase the temperature of boiler infinitely. There will be some metallurgical limitations. Okay, there is some limit how high temperature should be in the boiler. Again, there is a limit how low temperature we can achieve in the condenser. So what is the idea behind it? See, so this is again saturation curve, and in this case we have 1 to 2, 2 to 3, 3 to 4, 4 to 1 is a ideal Rankine cycle or regular Rankine cycle. Now whatever area enclosed in this curve, under this curve, 1 to 2, 2 to 3, 3 to 4, that is called as network term. That is called as network. Now if you want to increase the efficiency, what you have to do? You have to increase the network. How to increase the network? Increase the area. If you increase this area, that means our efficiency will also increase. Area inside this curve, 1 to 2, 2 to 3, 3 to 4 to 1. Okay. So there is a one way. Either you increase the mean temperature of heat addition, or you decrease the temperature of condenser. The first one here, it is lowering the condenser pressure. Okay. So to take advantage of increased efficiency at low pressures, the condensers of steam power plant usually operate well below the atmospheric pressure. Last lecture I have told you the pressure in the condenser is about 10 kilopascal generally. It is below 1 atmospheric pressure. 1 atmospheric pressure is 100 kilopascal, like around 100 kilopascal. In the condenser, pressure is about 10 kilopascal. So there is a lower limit to this pressure depending on the temperature of cooling medium. So as you can see here, in this case, they have lowered the condenser pressure. So simultaneously temperature will also decrease. So new curve we have here, it is 1 dash to 2 dash, 2 dash to 3, 3 to 4 dash, 4 dash to 1 dash. So you can see the area is shown by pink color. This is the increase in area. As the area is increased, the net work done will also increase and efficiency will also increase. But there is a side effect. Lowering the condenser pressure increases the moisture content of steam at the final stages of turbine. Now you can see here, point 4 was initially at dry saturated condition. That means dryness fraction was 1. All the water at point 1 is converted into steam at point number 4. But if I lower the pressure of condenser, new point is 4 dash. Now 4 dash point lies in the wet region. Lies in the wet region. That means it is a combination of steam plus water. And as I told you before, if there are some water particles in the steam which falls on the blades of the turbine, in that case there will be corrosion to the turbine. The effect of lowering the condenser pressure on the ideal Rankine cycle. Okay, so in this case the net work done increases. Now that was the first one. So please draw this diagram. It's very important. Give the title, how we can or increase, or just write down this, how we can increase the efficiency of Rankine cycle. In that, first write down lowering the condenser pressure and draw this diagram. Whatever increase in area, which is shown here by pink color, you show by hatch lines. Okay, incline hatch lines. Okay, completed. So first method to increase the efficiency is lowering the condenser pressure, which lowers the condenser temperature also. There is an increase in area, net work done increases, and efficiency increases. So they have shown this area by pink color. You show it by incline hatch lines. Okay, shall we move forward? Okay. So, okay. So today, I was not able to come to college because of some problem. So today we could not be able to take offline lecture, but next lecture will be offline. Okay. So students, others also try to attend the college in offline mode, because there is a difference in understanding in online mode and offline mode. In offline mode, you can ask or you can interact easily. In online mode, it has some limitations. So try to attend the college physically, others also, right? Okay. Now next method to increase the efficiency of the Rankine cycle is superheating the steam to high temperatures. Okay. What is the superheating? We have a subcooled liquid on the left side. We have wet steam inside the saturation curve. And the right side, we have a superheated steam. So if we increase the temperature of steam above saturation temperature, that is a superheated steam. Both the net work and heat input increases as the result of superheating the steam to higher temperature. How? So see, initially the curve was, so as I am explaining, you draw this curve also. So initially the Rankine cycle was 1 to 2, 2 to 3, 3 to 4, 4 to 1, as easy as it is. Now If I superheat the steam, so point 3 will now move towards the point 3 dash. Then again expansion in turbine, point 4 will also shift to point number 4 dash. So new cycle is 1 to 2, 2 to 3 dash 2, 4 dash 2, 1. So as you can see, there is an increase in area. Okay, which area I'm talking? Area inside this curve. Which curve? 1 to 2 to 3 to 4 to 1. याच्यात जो area आहे, that is a net work done. If I superheat the steam, there is an increase in area. They have shown by pink color. You show it by inclined hash lines. Okay. The overall effect is an increase in the thermal efficiency since the average temperature at which heat is added increases. Superheating to higher temperatures decreases the moisture content of the steam at the turbine exit, which is desirable. This is again another advantage. Apart from efficiency, as you can see, point number 4 initially was at inside the curve. That means it is a wet steam. Wet steam is not desirable for turbine. So if I superheat the steam, point number 4 will shift to point number 4 dash. So at number 4 dash, the dryness fraction is more compared to 4. So here we can say that it is desirable. The temperature is limited by the metallurgical consideration. Yes, because turbine blades made up of maybe steel or other alloys, they must have some melting point. If we exceed that temperature of melting point, then the blades will damage. Presently, the highest steam temperature allowed in the turbine inlet is about 620 degrees Celsius. So this much highest temperature you can achieve. So note down this value also 620 degrees Celsius. This might be asked in MCQ examinations. Okay, so draw this figure and highest temperature also you mention as it 620 degrees Celsius. So this is the second method of increasing efficiency by superheating the steam. Okay, completed. Right. Next method of improving the efficiency, here it is increasing the boiler pressure. Okay, so first two was lowering the condenser pressure, second was superheating the steam. Now next is increasing the boiler pressure. Okay, so again see here the initial curve here for the Rankine cycle is 1 to 2, again 2 to 3, and 3 to 4, 4 to 1. This was the initial curve of the Rankine cycle. The inside area of this Rankine cycle, that is a net work done. Now we want to increase the efficiency. So here another method is suggested, that is increasing boiler pressure. Now boiler pressure is increased, that means 0.2 will shift to 0.2 dash and 0.3 will shift to 0.3 dash. Okay, so this way we achieve the new points. So new curve will be 1 to 2 dash, 2 dash to 3 dash, 3 dash to 4 dash to 1. Okay, now here we cannot confidently say that efficiency may increase. Okay, you can see here though area in the vertical direction has increased, so this pink area, but there is also decrease in area on left side. Okay, previous case मध्ये कसं होतं, प्रिव्हियस केस आपण जर बघितले त्यामध्ये आपण डेफिनेटली सांगू शकत होतो की सर यस एरिया वाढत चाललेला आहे, that means network is increasing and efficiency increasing. But in this case we cannot confidently say that the area is, the net area is increasing or decreasing. So based on these calculations we have to decide whether the efficiency is increasing or decreasing. So for a fixed turbine inlet temperature, the cycle shifts to left and the moisture content of the steam at the turbine exit increases. So as you can see, initially 0.4 was nearer to dry saturation curve, but in the next or in the new point here it is 4 dash, which is inside of the curve. So Dryness fraction of 4 dash is obviously less than 4. Here the moisture content is more at point number 4 dash. So it is not desirable. Okay. The increasing boiler pressure not only decreases net work done, but also increases the moisture content. Okay. But this side effect of moisture content can be corrected by reheating the steam. Okay. Reheating steam म्हणजे काय करायचं? आता तुम्ही समजा 2 to 3 dash ला गेला, 2 dash to 3 dash. परत तुम्ही इथं फर्स्ट टर्बाइनला स्टीम पाठवली, राईट? त्याची थोडी एनर्जी कमी होईल and let us say it comes to this point. Again, you will pass through the boiler and again it will be reheated. So that is the meaning of reheating. Again it is reheated and then again it will pass through second turbine and then it is collected at the condenser inlet. Okay. What is reheating? What is regeneration? That we'll see in the next slides. So today many modern power plants operate at a supercritical pressure, that is a 22.6 megapascal, right? We have seen. So this is the saturation curve. The summit point here it is, or the apex point here it is critical point. Okay. At critical point, what happens? We need not to give the latent heat. The liquid is directly converted into dry steam. And have thermal efficiencies about 40% for fossil fuel plants and 34% for nuclear power plants. Most of the power plants nowadays, if you see Japan, if you take example of Japan, most of the power plants in the Japanese or Japan, they operate on supercritical pressure. That means they operate pressures above critical point. And some plants in the recent years have also started working on ultra supercritical pressure. So here, as you can see, if we operate above the critical point, the need of latent heat is eliminated. So point number 2 is boiler inlet. At critical pressure, this liquid is directly converted into steam at point number 3. Then again 3 to 4 turbine, 4 to 1 condenser. So draw both the diagrams. First give the title increasing boiler pressure and draw this diagram. Second, give the title supercritical Rankine cycle and draw this diagram. So draw this diagram first, increasing the boiler pressure. So this shows, so on one part there is increasing network, but on other part there is also decreasing network. So this problem can be eliminated by reheating the steam. Now you can increase the boiler pressure above the critical point also. So those are called as supercritical boilers. If their limitation is about 25 megapascal, but if you go above 25 megapascal, these are also called as ultra supercritical boilers. Okay, so draw this diagram also. Supercritical Rankine cycle. You can show the saturation curve, critical point, and if the boiler pressure is above critical point, this will be a supercritical Rankine cycle. So please draw, otherwise you will not be able to remember or recollect your memories at the time of examination. Okay. 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 So everybody completed up to this point. So let me recap once again. How to improve the efficiency? Either you can lower the pressure of the condenser, or you can superheat the steam, or you can increase the pressure of the boiler. Okay. So increasing the pressure of the boiler, there is also network increase in the network, but also decrease in the network. This decrease in network problem can be eliminated by reheating the steam. That is we are going to study. And another special type here it is supercritical Rankine cycle. That means the cycle in which the boiler pressure is above critical pressure of water. What is the critical pressure for water? It is 22.06 megapascal. Okay, right. Now, as I discussed previous, the reheat cycle. So ideal reheat Rankine cycle. Okay. So actually this point is was eliminated in the previous syllabus, reheat and regeneration. So, but we'll cover it because it is very important, because most of the power plant nowadays they like generally involve reheating the steam. So how can we take the advantages of increased efficiency at higher boiler pressures without facing the problem of excessive moisture at the final stages of turbine? आता आपण प्रिव्हियसली बघितलं की ठीक आहे, या केसमध्ये तुम्ही बॉयलरचं प्रेशर वाढवलं, त्यामध्ये 0.3 डॅशला शिफ्ट झाला, 4 डॅशला शिफ्ट झाला. Now at the 4 dash, the moisture content is more compared to point number 4. Moisture content is not desirable for turbine. So in that case, we can go for the reheating. So there are two ways: superheat the steam to very high temperatures. It is limited metallurgically. तुम्ही जास्तीत जास्त एका ठराविक टेम्परेचर पर्यंत जाऊ शकता. और एक्सपांड द स्टीम इन टर्बाइन इन 2 स्टेजेस. पहिल्या स्टेज मध्ये एक्सपांड करा, परत त्याला रिहीट करा, and then reheat in between. Okay, so this is explained with this schematic diagram. So you can see here there is this boiler is there, steam is coming out of boiler. First it is passed through the high pressure turbine. Then what happens? Its enthalpy decreases. Again it is reheated or supplied to boiler. It is reheated, and this reheated steam is again supplied to low pressure turbine. Here again work is produced. Enthalpy of steam decreases. This steam is then passed to condenser, in which the latent heat is lost, and steam is converted into water. This water is passed to pump. Pump increases the pressure of water to the boiler pressure. Then it is supplied to boiler. Okay. So this way, this cycle will work. Let us see the TS chart here. So initially, 1 to 2, you already know pumping. 2 to 3 is a boiler. Then 3 to somewhere should have been here the point outlet of turbine. Then 4 to 1. Now in reheat, what will happen? 3 to 4, this will be high pressure turbine. Okay, 4 will be the outlet of high pressure turbine, then it is again reheated. So you can see 4 to 5 is a reheating, and at 5 it is inlet to low pressure turbine. Steam passes through the low pressure turbine 5 to 6, and 6 is the outlet of low pressure turbine. Now you can see work is produced in two stages. Okay, work is produced in two stages. First is high pressure, then there is low pressure. Then again 6 is the inlet to condenser. 6 to 1 is a condensation. Steam is converted into water. Water is again pumped in the pump from 1 to 2. Okay, so draw this both the diagrams. This is related to reheating. So why we are going for reheating? Because in order to increase the efficiency, we want to increase the boiler pressure. If we increase the boiler pressure, there are chances of moisture at the turbine outlet. In order to eliminate moisture at the turbine outlet, we are going for the reheating. So see here, in this case, Q in, that is Q's heat supplied in the boiler will be Q primary. Primary means H3 minus H2, and reheat, that is H5 minus H4. So that means amount of heat is supplied to steam in the boiler. Turbine outlet will be, or the net work done will be here, work done in turbine number 1 plus work done in turbine number 2 minus work done in the pump. So that will be net work. Turbine work will be turbine work 1, turbine work 2. Turbine number work 1 will be H3 minus H4, this one, and 2 will be H5 minus H6. Okay, so write down. The ideal reheat Rankine cycle. Draw this diagram and draw this TS chart also. So one student has raised hand. Any question? So some student had raised her hand. Any question? Please draw the diagrams, board diagrams. Okay, completed. Any problem? I hope. Any problem up to this point? Now, who will tell me what will the efficiency of a reheat Rankine cycle? What will be the efficiency of reheat Rankine cycle? So the efficiency, what will be efficiency here? So this will be again same net work done. This divided by the Q in the Q in. Now Q in is here already, S3 minus H2 plus H5 minus H4. Okay. Net work done will be this turbine work out minus work required for the pump. So this will be net work done, right? So net work done will be total turbine work minus pump work divided by QA. So that will be the thermal efficiency of the reheat Rankine cycle. So write down this formula also. So elaborate this formula actually. So this will equal to what? So write down this H3 minus H4 plus H5 minus H6. This will be total work done in the turbine minus H2 minus H1, that is the pump work, divided by Q in H3 minus H2 plus H5 minus H4. Okay, completed. Completed. Have you completed? Okay. So see here, in this example, only 2 turbines are being employed, but in practical, there may be 3 or 4 turbines also, or 5 or 6 turbines also. So that way the reheating will take place. So only here you can see 2 spikes are here. Instead of these 2 spikes, you can observe multiple spikes also in the case of actual power plants, right? And the last method to increase the efficiency of the power plant is ideal regenerative Rankine cycle. So there are always 2 basic concepts, reheat and regenerate. Reheatचा उद्देश हाच होता की टू सुपरहीट द स्टीम इन मल्टिपल स्टेजेस. रिजनरेटिव्हचा उद्देश हा आहे की टू यूज द एनर्जी ऑफ स्टीम टू हीट द वॉटर इन द बॉयलर. म्हणजे टर्बाइन मधून बाहेर पडलेल्या स्टीमची थोडी आपण एनर्जी वापरतो कशासाठी, बॉयलर मध्ये वॉटर हीट करण्यासाठी. ठीक आहे. रिहीटचा उद्देश होता सुपरहीट करण्यासाठी. रिजनरेटचा उद्देश आहे बॉयलर मधली एनर्जी कंटेंट वाढवण्यासाठी. ठीक आहे. सो heat is transferred to working fluid during the process 2 to 2 dash at a relatively low temperature. This lowers the average heat addition temperature and thus the cycle efficiency. आता होतंय काय ह्या केसमध्ये, बॉयलर मध्ये टेम्परेचरचे लिमिटेशन्स असतात. टेम्परेचर कमी असेल तर सायकलची इफिशियन्सी देखील कमी होते. सो वी हॅव टू इन्क्रीज द मीन टेम्परेचर ऑफ heat addition. In steam power plants, steam is extracted from turbine at various points. This steam, which could have produced more work by expanding further in the turbine, it used to heat the feed water instead. म्हणजे काय करतो आपण, टर्बाइन मधूनच एक बायपास थोडी करतो, स्टीम बाहेर काढतो. ती स्टीम परत आपण कशात पाठवतो, बॉयलर मध्ये पाठवतो. तिथं काय होतं, टेम्परेचर वाढतं बॉयलर मधलं, त्यामुळं टोटल सायकलची इफिशियन्सी देखील वाढते. The device where the feed water is heated by regeneration, it is called a regenerator or a feed water heater. So we have a feed water pump, right? So it will pump the water to the boiler pressure and it is supplied to boiler. So feed water pumpला जे पाणी असतं त्याला आपण म्हणतो feed water. So water coming to feed water pump, it is called as feed water. And by using the energy of steam, which is taken out from the turbines, we are going to increase the temperature of water. म्हणजे बॉयलरला येणाऱ्या वॉटरचं टेम्परेचर आधीपासूनच जर जास्त असेल तर परत त्याला सुपरहीट करण्यात आपल्याला जास्त एनर्जी खर्च करावी लागणार नाही. ओके, जर बॉयलरला येणारं टेम्परेचर, वॉटरचं टेम्परेचर जर पहिल्यापासूनच जास्त असेल तर आपल्याला परत त्याला सुपरहीट करण्यामध्ये जास्त एनर्जी खर्च करावं लागणार नाही. सो दिस इज द मेन ऑब्जेक्टिव्ह ऑफ द रिजनरेटर. वी आर इन्क्रीजिंग द वॉटर टेम्परेचर कमिंग टू द boiler. So a feed water heater is basically a heat exchanger where heat is transferred from steam to the feed water either by mixing of two streams. म्हणजे डायरेक्टली तुम्ही स्टीम वॉटर मिक्स करा, त्यामध्ये देखील वॉटरचं टेम्परेचर वाढेल, और बाय मिक्सिंग देन सेपरेटली. दॅट मीन्स एका पाईप मधून तुम्ही वॉटर पास करा, त्याच्या सराउंडिंग मध्ये तुम्ही स्टीम पास करा. सो देर विल बी heat exchange and the temperature of feed water, that is water coming to the boiler, will increase. So in next slide there will be diagram. So this is a open feed water heater system. Okay, आता यात काय होतं आपण स्टेप बाय स्टेप बघूया. बॉयलर मधून एक स्टीम येते, राइट? स्टीम इज पास टू टर्बाइन, राइट? Now in this case what happens, some part of steam is extracted. Some part of steam is extracted in turbine after doing work. That is, suppose Y content, Y percentage of steam is extracted. This high pressure, high temperature steam, it is passed to open feed water heater. Open feed water heater म्हणजे डायरेक्ट स्टीम आणि तुम्ही फीड वॉटर मिक्स करणार आहे. आता राहिलेली स्टीम पूर्ण एक्सपान्शन झाल्यानंतर टर्बाइनच्या आउटलेट मधून बाहेर येईल. दॅट इज 1 minus y, because y is been taken out here. So remaining 1 minus y content is taken. So this is a low pressure, high temperature steam. It is passed through condenser where steam is condensed to water. Here this water is supplied to pump 1. Pump 1 will pump it to certain pressure, right? So here condenser pressure is below atmosphere. So pump 1 will increase the pressure to at least atmospheric pressure. Then this water is supplied to feed water heater. Okay, so this water is called as feed water. Here this feed water is mixed with this steam coming out from turbine. Because of heat transfer, the temperature of this feed water will increase, and this high temperature water is passed through pump number 2. It is now pumped to boiler pressure, and this will be passed to boiler. Okay, so what is the objective here? To increase the temperature of feed water. As we increase the temperature of feed water, there is a less effort to be taken to superheat the steam in the boiler. So an open or direct contact feed water heater is basically a mixing chamber where the steam extracted from the turbine mixes with feed water exiting the pump. Ideally the mixture leaves the heater as a saturated liquid at a heater pressure. म्हणजे हे the temperature एवढं वाढतं की the water becomes saturated, that is liquid saturated. मग बॉयलर मध्ये फक्त तुम्ही लॅटेंट हीट ऍड करायची and it will be superheated. ठीक आहे. So initially you can see, इनिशियली आपल्याला काय करावं लागतं, 1 to 2 पंपिंग करायचं आणि मग हे वॉटर बॉयलर मध्ये जाऊन मग ते सुपरहीट होणार. पण नवीन केस मध्ये काय होणार आहे, इट विल बी इटसेल्फ सॅच्युरेटेड and then you have to just add the latent heat and then it will be superheated. So there is this diagram of regeneration is given. So 1 to 2 is a pumping, right? So condenser pressure is below atmospheric. We are increasing the pressure to atmospheric. 2 to 3 here it is a heating in the open feed water heater. Again 3 to 4 is pumping, that is pumping number 2. Pump what the pressure of water or the hot water, it is increased to boiler pressure. 4 to 5 is heat addition in the boiler. Okay, so आपण हे open feed water heating केल्यामुळे तुम्ही बघू शकता की this energy to be added for superheating decreases. आधी हा जो एवढा मोठा गॅप होता, now it is decreased to this much. Now again 5 is the entry to the turbine. थोडंसं एक्सपान्शन झाल्यानंतर at point number 6, y amount of steam is extracted and this steam is passed to feed water heater. Again, remaining heat, that is 1 minus y, it is expanded fully at point number 7. 7 is the entry to the condenser. 7 to 1, condensation takes place, steam is converted into water. Okay, so this way the cycle will be completed. So draw this schematic, also draw this TS diagram. So draw both the diagrams. Now in this case, how to calculate the efficiency? So again, efficiency formula is W net divided by Q in. Q in here it will be H5 minus H4. Okay. Enthalpy of outlet steam divided minus enthalpy of water incoming to boiler. So this is very simple. Q in is simple. What about net work done? Net work done will be net turbine work minus net per pump work. What will be net turbine work? Net turbine work will be H5 minus H6, that is first expansion before extracting the steam. म्हणजे ज्यावेळेस आपण ही y amount steam करतो त्याच्या आधी जे काही वर्क डन झाले, so that is a H5 minus X6. After steam is extracted, the remaining steam is 1 minus y, and in this case 1 minus y mass into H6 minus H7. Okay, so that will be the total work done in the turbine. What will the total work done in the pump work? Pump work 1 and pump work 2. What will the pump work 1? In this case, the mass of water is 1 minus y into pump work 1 plus pump work 2. Okay, and how to calculate pump work? Specific volume into pressure drop. So pump work 1 will be specific volume 1 into in bracket P2 minus P1, and pump work 2 will be specific volume V3 into in bracket P4 minus P3. Okay, so write down these formulas. So now you know total turbine work, total pump work. Net work will be total turbine work minus total pump work divided by Q in, that will be the thermal efficiency. Okay, so the thermal efficiency again in this case will be equal to W net divided by Q in, right? So W net, we all know what will be W net. W net will be equal to W T net minus W P net. Okay. And divided by Qn. Qn is H5 minus H4. Write down this formula because we are going to solve the numericals. At that time, it will be very helpful. Draw the figures first. Draw the schematic of open feed water heater and this TS diagram. Okay. Next variation is there in this case, that is a closed feed water heater. In that case, the water will flow through the pipes and it will be surrounded by steam. So write down all these formulas and figures. So draw this, both the diagrams, draw this and write down the formulas. Net efficiency will be W net divided by QA. W net will be total turbine work minus total pump work. There are some combined power plants also where reheat is also taking place and regeneration is also taking place. म्हणजे तुम्ही 2-3 स्टेप मध्ये स्टीमला रिहीट करू शकता प्लस स्टीम एक्स्ट्रॅक्ट करून फीड वॉटरला तुम्ही हीट देखील करू शकता. तर तुम्ही प्रॅक्टिकल जे आपण ज्यावेळेस बघू पॉवर प्लांट त्यावेळेस तुम्हाला कळेल की there is reheating also and there is a regeneration also. Another important thing which I discussed with our honorable HOD Wankar is that can we arrange industrial visit for this semester? So sir said that there is no such official statement from university, but as a student you may try. You may visit Wankar sir, ask him about industrial visit. Like for this subject, apply thermodynamics, we can go for nearby sugar factories or other factories where boiler is installed. We can see the working of boiler. Last batch or your seniors which are in the final year, so last to last batch, they went for this nuclear power plant in the Tarapur. So great efforts were taken by those students at that time, also faculties. A very good industrial visit was arranged at that time. Students got opportunity to see a nuclear power plant in the Tarapur. Okay, so that was very quite often thing happen in the institute. Though there are some restrictions nowadays, but still you can visit Honorable HOD. You can ask him for the industrial visit. If we can go, no problem. We'll arrange. Okay, completed. Right. Last one here it is. Last one for today. It is closed feed water heater system. Okay, closed feed water heater system. So as I told you, previously it was open feed water heater system. That means heat was directly supplied to water and these are mixed together, right? So here we have a open feed water heater, in which case this steam from turbine is directly mixed with water and the temperature of water is increased. But here we have closed feed water heater. Here we can see the steam coming out from the turbine. It is passed to a closed feed water heater. The water coming from condenser, it is first pumped by pump 1. This pumped water is passed through series of tubes. Okay, it is passed through pipes or tubes, and this steam is passed outside of tubes. There is a heat transfer takes place, and this water is heated. The steam gets condensated and it is collected at the basin. This collected water at the basin is again pumped to mixing chamber. In this case, this water which is collected at basin and this water coming out from tube, these are mixed together in the mixing chamber. Then this water is, this hot water is again hot and pumped water is passed to the boiler. Okay, previous case फार सोपी होती, यामध्ये steam इथून काढली, इथून water घेतलं and these are mixed together. But in this case, what is happening? Steam is extracted, water is passed through pipes, water is heated, steam gets condensated and it is collected at the basin. This water is collected, it is pumped by pump number 2 to mixing chamber. So here we have water coming from tubes, here we have water which is pumped. These are mixed together. Net effect is to increase the temperature of feed water. This high temperature feed water is supplied to boiler. Okay. Now see here the TS diagram. So 1 to 2 we already know, that is a low pressure pumping. Then what happens? These are passed to the closed feed water heater. These are passed to closed feed water. 2 to 9 is the increase in temperature of water passing through tubes. Then at point number 3, we have collected the water. It is pumped to pressure 4. Okay. Now at mixing chamber, from one side 9 is coming, other side 4 is coming. Resultant we have point number 5. So point number 5 is the inlet to boiler. The temperature is heated and it is superheated to point number 6. Again at this 6 point is the inlet to turbine. The steam is expanded up to point number 7. Then some part of steam is extracted. It is passed to point number 3. Remaining steam is further expanded and we get at point number 8. Point number 8 is entry to the condenser. The steam is condensated to water and then cycle will repeat. So draw this diagram, schematic, and draw this TS diagram also. So here net effect is to increase the temperature of feed water heater. Okay. So draw the schematic, draw the TS diagram. What will the efficiency here again? Efficiency will be net work done divided by Q in. Q in will be the heat supplied in the boiler. Okay. That will be H6 minus H5. What will be the pump work? Pump work will be sorry, what will the turbine work? Turbine work will be, let us say the y amount of steam is extracted here. So y, so it will be H7 minus H6 plus 1 minus y, H8 minus H6. So this will be the turbine work. Pump work will be pump work 1 plus pump work 2. Okay. So maybe I'll write down. So efficiency in this case will be equal to W net divided by Q in. W net, you know, that is W, that is turbine work minus pump work divided by Q in. What is a Q in here? Q in here it will be H6, that is the steam enthalpy, minus water enthalpy, that is H5. Very simple. What will be the turbine work here? Total turbine work will be, let us say y amount of steam is extracted here, and remaining here it is 1 minus y. Okay. So first it will be H7 minus H6, that will be up to the steam is extracted. After extraction of steam, it will be 1 minus y, that is mass flow rate of steam, and this will be into H8 minus H6. Okay, so this will be H7, sorry, H7 minus H8. This will be total work done in the turbine. What will the total pump work? Pump work will be equal to WP1 pump work 1 plus pump work 2. In this case, again, you have to multiply pump work 1 by mass flow rate. So I'll erase this one. So, okay. So this will be equal to 1 minus y, right? 1 minus y into pump work 1 plus pump work. So here this water is collected and this is y. Okay, so this into y. Okay, pump work 2. Okay, then you calculate, you take the difference, total pump work, sorry, total turbine work minus total pump work, that will be net work, and divided by Q in, that will be your efficiency. Okay. Again, I will explain this part. 1 to 2 is water is pumped in the pump 1. Then it is passed to closed feed water heater where it is heated. So it is heated from 2 to 9. Again, we have point number 3. In point number 3, it is pumped to point number 4 with pump number 2. So at the mixing chamber, we have 2 inlets, point number 9, point number 4. These are mixed together. We get a final temperature, that is point number 5. Then this 5 is passed to boiler. This is superheated to point number 6. Then 6 is passed to turbine. It is first expanded up to point number 7. Then Y amount of steam is being extracted. It is passed to point number 3. Remaining steam is further expanded up to point number 8. Point number 8 is the entry to the condenser. 8 to 1 is a condensation takes place. And again at point number 1, we have water. So this way, the regeneration in the closed feed water heater, closed feed water heaters will take place. Okay. So quickly, I will recap. I hope all have completed this diagram. Quickly, I will recap today's whatever we have taken. So today we started with how we can improve the efficiency of a vapor power cycle. First was to lower the condenser pressure. So if the area is increasing, definitely the network is increasing. So efficiency is also increasing. Second was reheating the steam, which was also very good. Third was by increasing the boiler pressure. So here there was a confusion whether the network is increasing or decreasing. There is also decreasing network. So this can be eliminated by reheating the steam. Then we have seen the supercritical Rankine cycle in which the pressure inside the boiler is above the critical point of water. Then we have seen two other methods commonly used, that is reheating and regeneration. In reheating, first steam is expanded in high pressure turbine, then again it is reheated in the boiler. Reheated steam is passed to low pressure turbine. So there is a two-stage work done is produced. Next was regenerative cycle. In regenerative, what we do, we increase the temperature of feed water heater with the help of steam which is extracted from the turbine. So here we have seen the steam at the turbine after some expansion is extracted. It is passed to a feed water heater. The remaining steam, it is condensed, it is converted into water. This water is passed to feed water heater. There are two choices. Either you can do direct mixing or you can do indirect heat transfer. So direct mixing means steam plus water, temperature of water will be increased and this is passed to boiler. Most commonly used method is closed feed water heater. In this case, steam is passed to the closed feed water heater. Water is passed through tubes. Heat exchange takes place. This steam is condensed. It is collected at basin. This is again pump. So there is water coming through tube, and there is this water which is pumped. These are mixed together, and finally this water is supplied to boiler. Right? So a system can be as complex as this much also. There will be multiple open feed water heaters, multiple closed feed water heaters. So depending on the application, the system is being designed. Okay. Now in next lecture, we'll go for some numericals, right? And we'll see some of the advanced topics like cogeneration, then the combined gas power cycle. Then we'll see the efficiency, how to calculate overall efficiency in the case of cogeneration. Okay, so these are some advanced topics we'll cover at the end of the chapter, but first we'll cover some numerical part. As we solve the numericals, your understanding about the vapor power cycle will be more clear. Okay, so any doubt? So you can enter your attendance in the chat box. If you have any doubt, you can ask, or you can enter your roll number in the chat box for your attendance. Okay, so with this, we'll stop today. Thank you for attending. See you in next lecture.